Okay, so just from that research review, I've got a couple of graphs here to show you. So this first one is a modified leg press, okay? So they looked at blood pressure, intrathoracic pressure, and the force of contraction, the amount that they could lift. So here what we're looking at is their blood pressure, concentric, isometric, and eccentric. So you see that it makes this upside down V. So concentric and eccentric were lower pressures than isometric, and the blood pressures seem to be the same. So concentric, isometric, and eccentric, the blood pressure seemed to be the highest for the isometric, again here at 82.5%. So, that's for the blood pressure. That's for Jack. That's relevant for Jack. Okay, this is the weights lifted. So concentric, isometric, and eccentric. So what we're looking at here is that concentric is the lowest percentage of MVC that they can generate, and then isometric and eccentric here. And so you'll see that no matter at 50, 70, or 82.5%, you'll see that the concentric was the lowest out of all at the three weights. Yep. And then maximum intrathoracic pressure. So this is the one that we're looking at. Intrathoracic pressure and intra-abdominal pressure often go together. They're not always exactly the same. However, it's interesting to see because we were talking about Valsalva and we know the pressure goes upwards in a Valsalva. So this is the most amount of pressure they generated intrathoracically. They reported 95 plus or minus 5, so 90 to 100 millimeters of mercury was a max. So what you'll see here is that at 50% of the load, what you're seeing is that they're at a relatively low percentage, let's say 20% of the pressure that they can generate for a maximum pressure. And then here, what you're looking at 70%, it's the same sort of thing. You're looking at 40, 50%. And here at the 82.5%, we're now at a much higher percentage, like maybe a 60, 70%. So as the weight goes up, the amount of intrathoracic pressure needed to generate goes up. Now, what about fatigue? So I said earlier that fatigue makes a difference. And here's what you see. They're doing a set of 8 squats at the 8 RM weight. So, they've got no reps in reserve. And what you're seeing is they broke it down into pairs of reps. So reps 1 to 2, reps 3 to 4, 5 to 6, and 7 to 8. And that's what you're seeing here. So for reps 1 and 2, the relative pressure is lower than you're going to see at the end, towards the end of their set. And this is 8 squats at 8 RM. This is like 100% effort. So what you're seeing here is a trend of increasing pressure as the reps go on in the set. But also, they compared that to people doing it with a belt and without a belt. And what you're seeing is that they can't lift as much, number one. Number two, they're generating less pressure without a belt than they're doing with a belt. Now, it's important to note, again, it's only 5 guys, only 5 men. But this is the overall pressure with a belt and without a belt. You can see there's a significant difference. Again, here, a difference of the maximum pressure that they generated during the set. With a belt, the maximum pressure was higher than the maximum pressure without a belt. And then on the down phase of the squat, you can see that the pressure wasn't as heavy, it's just less work. And so less pressure in general compared to the up phase. But again, there's a significant difference between the belt and the no belt situation here. And the up phase, and the up phase is where we tend to get the sticking point, where you're going up. It's around 90 degrees of knee bend. And so I think that's why the pressure is higher here on the up phase, where the hardest part of the lift is. And again, higher compared to the up phase without the belt. So hopefully those 2 graphs help to show you what I was trying to say about the belt being more pressure than no belt, and the thoracic pressure, the pressure generated increasing as the weight goes up.